Well, hello guys and welcome back to Mr. G Physics, the channel that can help you to improve your marks in physical sciences. Here's Mr. G, and this time we're going to continue working for the grade 11 related to electromagnetism. Last time we look at how is the magnetic field generated around a conductor in which an electric current is flowing. This time we're going to go a little bit further and we'll speak about Faraday's law, and we are going to do another experiment to see Faraday's law. Faraday's law. Now, we know that in 1820, Christian Ørsted discovered that around a conductor in which an electric current is flowing, a magnetic field is generated. We saw it in an experiment in the previous video. Now, later on, in 1824, Michael Faraday discovered that, well, the other way could be also done. If you have a magnetic field, will you be able to produce or to generate an electric current? And then Faraday did certain experiments to arrive to the conclusion that yes, if you have a magnet or a magnetic field, you can induce or generate an electric current. In actual fact, this is how the current that you receive at home is generated. This with a generator, and is by using Faraday's law related with magnets and how with a magnetic field we can generate electric currents. So let's quickly go and see how is this experiment done. And guys, here we have all the apparatus we're going to need for this experiment. If you look here, we have a coil. We need a coil. We already work with that one, so you know the coil. We need conducting wires. We have here some conducting wires. We're going to use a compass. Here is a compass. We need a magnet, and this is a galvanometer. Now, the galvanometer is an instrument used to measure small amount of alternating current. So it will have the needle right in the center, and it will be moving in both directions because we are working with alternated current. Alternated current is when the current changes direction. So that is what we're going to have here. So this is the coil, and we are going to do the following. No battery is needed because we're going to generate, we're going to make electric current, and the only thing we're going to need is a magnet, and we're also going to need this coil. So note the following. I'm going to connect one side of the coil with these conducting wires. For instance, the negative could be at the bottom. It doesn't really matter on what side you are going to connect. So note, these conducting wires are connected to nothing, only to this specific coil, which is a solenoid. Somehow you can see it have many turns inside there. It's not just one coil, but you can see it's a rotation of many coils, a little bit thick or a little bit big in terms of the area. So here we have a negative side, and we have here a positive side on the galvanometer. And then what we are going to do is we are going to see how can we generate a current or induce EMF with this specific magnet and coil. Okay, so it's quite simple. We are going to approach, and this one is the same thing as Faraday did. He used a magnet, and then he started playing with the magnet and coils to see what happened. So eventually he noticed that if he approached the coil in certain way, then the needle will deflect there. So note, because the current generated here is quite small, but if I do this one, you can see the needle is now deflecting. Now note, I cannot move around because the deflection is extremely small. I have to move in and out the magnet of the coil there. Well, I zoom it a little bit so you can see it better. And let's see again. Look at the needle of the galvanometer. No tricks here, only the coil and the magnet. So if I move it, you can see it deflects a little bit. There you can see it deflects a little bit. This one is moving because I'm touching it by accident. Nothing to do with I'm moving that one with the magnet. This one is copper. It cannot be attracted by the magnet. You can see there. Okay, so now if I do this one, I insert, you can see the needle deflect in one direction. So let's repeat that one. I reflect, and it deflects in one direction. So if I insert this side of the magnet, it's starting deflected in one direction. If I turn the magnet around and then I do the same, then it deflects in the opposite direction first. So note, this needle in one case is going to move to the right first and then to the left because it's turning direction. So let's see that one there. If I use this point here and I insert the magnet inside there, you can see it deflect in one direction. There you can see it's small, the magnetic field is quite small here, there we go, there, there. So if I turn around, then it moves in the opposite direction first. There we see. It's very small, but you can still see that there is a magnetic field generated in there. Okay, so guys, this one was Faraday's law. This is all Faraday did. He used a magnet to generate a magnetic field. You can see that it's quite small. The current we produce in here is small, but can you imagine if we have a big magnet and a big solenoid? We're going to speak about that one just in a minute, but this is the main things I wanted to show you there. Okay. Okay, so let's see what actually happened here. Let's go to Faraday's law. Now, this law says that the EMF produced around a loop, and this EMF produced is going to be with a Greek letter epsilon. This is epsilon, and it's a Greek letter, it's not an actual E. All right, now around a loop of conductor is proportional to the rate of change of magnetic flux. We're going to speak about magnetic flux in the next minute, but this one here is the rate of change in magnetic flux. Now remember, rate is when you divide by time, so it's how fast magnetic flux is changing. That is what we mean here by rate of change in magnetic flux through the area of the loop, and we're going to speak about that one right now. Here is the formula for Faraday's law, guys. The EMF, that E represents EMF, that is the EMF that is induced. Induced means being produced, being generated. Okay, so now is equal to minus, and now N is the number of turns in that specific coil that we're speaking about here. If we, for instance, go back here to the experiment, we can see that this, the number of how many coils are turning around here in this specific solenoid is what we're speaking about, the number of turns. That is the number of loops or coils in the specific solenoid. Okay, now what else? We say we're going to speak about magnetic flux. Now what is magnetic flux? Magnetic flux, which is a Greek letter phi, represents the number of field lines that cross a specific area. So if we go back to the experiment, for example, real fast here, we're speaking about the number of field lines as I approach the magnet to the coil, the number of field lines that is going to cross this specific coil inside. That is what we speak about magnetic flux. That is magnetic flux. The number of lines, as you can see here, that cross a specific area. Now we can calculate the magnetic flux. Magnetic flux can be calculated by B, and B is the magnetic field, which is the unit is Tesla. Is something new that you don't know here. The A is for the area we're speaking about. In this case of the experiment, we have a rectangular area there. That is the area we're speaking about, and the angle between the magnetic field and the normal to the area. Now that could be a little bit tricky, so let's have a quick look here. If we go to this part here, now the angle is between the magnetic field and the normal to the area. So if the area is, for instance, this right angle, the normal will be that blue line that you can see there. So in this case of the experiment, the normal to the area will be the perpendicular line to that area, will be this line of that pen of mine. That will represent the normal to that specific area in this experiment. Okay, so when we approach the magnet, in this case, the angle between that magnetic field, this magnet, and the normal is going to be 0 degree. Okay, so that is in terms of the angle. Now, what factors will affect the induced EMF? Well, we have three main factors, and all of them are in the formula. The first is the strength of the magnetic field. How strong is the magnetic field generated by the magnet? All right, that is the thing. How can we increase or decrease that one? By changing a magnet, by using a stronger magnet or using a weaker magnet. That is the way of changing the strength of the magnetic field. Second, the number of turns in the coil. In the experiment here, if we go here, the number of coils, the more coils you have, the greater will be the EMF generated. And the other one is the speed at which I move in and out the magnet, or the other way around. I can keep the magnet and then move the coil. Guys, this one is in terms of Faraday's law. I hope you understand. I hope it helped with the galvanometer and the experiment. Maybe it's better to picture this one, compass 4, but we didn't actually use it. Guys, thank you for watching. Subscribe for the channel. I see you next time, Mr. G.